Statistics Part 2. Well, now we're going to have another production run, but these guys just aren't all together. The data is going to look a little different. The first sample is 11.5 grams, 9.0, 8.5, 11, and 10. Let's go take a look at the mean. Add them up, divide by 5, and you're right on the money. We get 10 grams. Compare that to what the target is. Your percent error is 0. Does that mean this assembly line did a good job? I think we better look at the mean deviation. Quick review, you want to take each one of these data points, subtract the mean. That's what we're doing here. Do the absolute value, add up all of those deviations, and then divide by how many of them we have. Here we have a deviation of 1.5. Here we have a deviation of 1, a deviation of 1.5, a deviation of 1, and there's no deviation here at all. When I add those deviations together and I divide by 5, I get 1 gram. Well, that means this group here is all over the place. I don't think I would want them making equipment for me if this is the best they can do. So this is way off. It tells me that the data is rather variable. This is much more consistent. So there's a difference between your error and how variable your data is. We can illustrate this with a little target practice. Let's say somebody shoots at target A and produces this pattern. Target B, target C, and target D. Which one of these targets represents the best accuracy? Think about that for a moment. I think most people are going to say D is the most accurate. Well, accuracy means how close are we to the bullseye? We say D is accurate because it's very close to the bullseye, and that means percent error is very low. But there's actually another target that's quite accurate, and you might find it hard to believe, but it is C. Take a look at this mark here. For mark here, there's another mark over here. There's a mark down below, well then there's another one up top. If you started to average all of these data points together, you're going to find out that they average out to be right about in the middle. So this one, on average, all the X's, average all the Y's, it's close to the bullseye too. So we would say it's accurate. But clearly there's a difference, and that is what we mean by precision. So I think a lot of people would say that D is also precise. If the data is close together, we would say that it has a low mean deviation. So is there another target that has precision? Take a look. It would be A. All of these data points are very close together. A is precise, but is it anywhere near the bullseye? No. So it's not accurate. What about C? It's accurate because it averages out to be on the bullseye, but it's not precise because the data is all over the place. Okay, what about B? It's not accurate, missed the bullseye. It's not precise, the data is all over the place. So which marksman here would you say is the best one? I think most people would say this one. But it's possible that this person here is actually quite good. There's just a problem. Every single time, the bullet missed the mark by about the same amount. What could cause that? Why would somebody purposely aim in the wrong place? I don't think so. They're probably aiming right here. I'm going to take a guess that the equipment could be off. The sight of the gun needs to be adjusted. We call that a systematic error. So it's better than the random error of scattering things around. So when we do labs, yeah, sure, we're looking for accuracy, but we would also like to have some good consistency. We're looking for precision as well. Hopefully this will give you something to think about when we do our lab work.